Hey everyone, and welcome to Interactive Stargazing this Thursday night, September 3rd. We've had a couple of really rainy nights, overcast times this past couple of weeks, so we're really looking forward to tonight and the next couple of weeks of clear skies. So right now we are looking up. Moon is starting to come up, so we're going to try and look at some of our dimmer objects first, resorting to those couple of deeper sky, or rather those stars and brighter things like planets later on in the session. So for now, we can start with something called the Veil Nebula, which is actually a supernova remnant. So what happens at the end of a very massive star's life is that it runs out of fuel at the core. So you've got this huge star, maybe 10 times the mass of the sun, maybe closer to 5 times the mass of the sun. And it's just this very, very massive star. The inside implodes and the outside explodes out into this huge supernova. And this casts gases all over the universe. This is actually where a lot of the gold and silver and iron, well, maybe not so much the iron, but at least those heavier elements that we find here on Earth, they're coming from places like this Veil Nebula. So if you think about just the sheer amounts of these heavier elements that we have here on Earth, we can actually look at where this came from in outer space and know that billions of these have had to happen over time. So we're going to go ahead and switch views to something that's similar to this Veil Nebula, except on a very small scale. This is called the Ring Nebula, and it's actually a much smaller planetary nebula. So instead of being a supernova remnant, the leftover of a star about 2 to 10 times the mass of the sun, this is going to be the remnant of a star about the same mass as the sun. So when we look at this, and we've got that image here, we can actually see a little bit of detail in that exploding gas. And that same thing was actually visible in that picture before, all that kind of veiny texture, almost like tendrils of gas. There is some structure to those gases. And it goes so far as actually corresponding to which gases are present in which areas. The very light gases, since they tend to expand a little bit faster, they're lighter, a little bit of energy makes them move a lot faster than a big heavy thing. That will make those light elements spread to the outsides. And so we can actually see a little bit of red coloration just along the outer edge of our Ring Nebula. And that's actually because that hydrogen is glowing red and the heavier elements within are glowing those deeper blues, and in some cases yellow as well. So that brings us from those planetary nebula to an object that's a little bit farther away from us, and this is something called M15. And so these planetary nebula are very cool because they show us what happens at the end of a star's lifetime. But these only exist in outer space for a surprisingly short amount of time. And we of course assume that on an astronomical scale, a very short amount of time is going to be a rather long time, and it's true. These structures can be visible anywhere from about 10 to 30,000 years after the explosion of that star. So we'll go ahead and, we can't quite see it, but there's a small remnant of one of these stars that exploded, and it had to have happened so recently, relatively 20,000 years ago, for us to still see that gas cloud expanding out, where some of these stars can live for billions of years. So there's also a little nebula nearby. And so we did have a question about some of the software and hardware that we're using to run this program. So I'll dive into that real quick while we're talking about these very distant objects. So you're seeing light that's coming from about 33,000 light years away from us. So at the very edge of our Milky Way galaxy, and those little photons are coming from stars and imprinting onto our CCD. So that's just a little chip in the back of our telescope, very similar to the camera that you'd have in your iPhone, but this one's called a Malincam. And so our Malincam color CCD transfers that image that comes from that telescope, and then we actually get a live view of that right here. So you're actually seeing raw digital data collected from a telescope. Now, the telescope itself is 14 inches across, and it's a motor-driven mount, so it can basically move from one area of the sky to another very quickly. We did have that view of the Godot Plaza not too long ago, and so it would be one of those telescopes that's mounted up on one of the pillars. So I'm going to go ahead and answer a couple of questions that we saw from the chat, and then we can maybe go a little bit further into this idea of these stars that are so far away. So we have, and I'm just going to go kind of backwards here. What happened to the star Betelgeuse? Now, there was actually some controversy at first as to what was really happening. So we see a star called Betelgeuse, and it's usually a very, very bright star. And it dipped in brightness a couple of orders of magnitude. So it was actually maybe 10 times fainter than we had seen it, previously. And so there's another star nearby in the same constellation of Orion, Rigel. Betelgeuse usually outshines Rigel, but it was very dim at this point. Then a paper was released that showed that there was actually a big dust cloud and probably an eruption of gas that was cooler. And so it blocked some of that light from Betelgeuse. And so from our perspective way back here, there's this big cold gas cloud that's blocking some of that view. So we'll go ahead and focus on a couple more of these comments we've had. We will be able to get all the gas giants and possibly Mars. We could keep our fingers crossed for that. There is a nebula in Cassiopeia, and I guess we could possibly try that, but the problem with that is that there's some moonlight. So we will go ahead and shoot for that. So Gamma Cassiopeia Nebula, and we'll go ahead and just see what we can do. While we're doing that, there is an object called M64. It's the Black Eye Galaxy, but unfortunately that's a little bit low on our horizon. So we probably can't do that tonight. The Eagle Nebula is definitely something we'll check out. So that's kind of going to segue from those distant stars to where they come from. And so we'll do the Eagle Nebula along with the Trifid Nebula a little bit later. I guess we're going to see if we can get that little faint nebula, but any longer than, maybe 15 seconds, and we'll go ahead and change over. So I think we want to do the Cat's Eye Nebula in a little bit. So we'll see how our little nebula worked real quick, the Gamma Cassiopeia Nebula. And it looks like we might not be able to get that one. So I think we're going to go instead with actually the Cat's Eye Nebula real quick. And that's related to that Ring Nebula because that's a planetary nebula. So for someone that just put in a question about planetary nebula, that would actually be the second example of which we saw the ring nebula before, and even like I mentioned in that big cluster of stars, there's a small planetary nebula up here. So really prolific objects, which is surprising given the fact that they only last for about 20,000 years. So that's kind of what I was referring to earlier, is that all these other objects, right? You're seeing a star, a galaxy, these things can last for billions and trillions of years. Well, maybe in the case of like white dwarfs and stuff, I guess the trillions was an overstep. But anyway, what I was basically referring to is that you can have these very old objects, and in comparison, 20,000 years, it's not that long. And so to be able to see as many of these, and there's over 1,000 in our Milky Way, means that a whole lot of stars explode all the time. And it just so happens that there's so many stars exploding that these relatively short-lived events are visible from here in the Milky Way. So we've got that Cat's Eye Nebula kind of knocking two birds with one stone. And we can go ahead on over to that Eagle Nebula. And right nearby, there's going to be something called the Swan Nebula. There's also the Trifid Nebula, even the Lagoon Nebula. So the region of space that we're looking at, and in comparison to our view from the Godo, this would be directly south. We are looking up toward the center of the Milky Way galaxy. And because there's such a big concentration of mass and stars and kind of the debris that makes those stars as well, you see a lot of these big clouds that tend to form new stars. So there's a very particular structure within here called the pillars of creation. And so you've got basically these little dark clouds that are silhouetted against the background radiation of the more distant cloud. So yeah, there's a lot more visible. You can see kind of those darker structures. Now, you may think that the bright parts are associated with the birth of a star, since stars are so much brighter. But the truth is that these gas clouds have to be very cold in order to make stars, because those molecules have to have very little energy so that they can get squeezed with enough density to turn into a star. So basically, we are looking at one of those regions of nearby star activity. Our eyes are only able to perceive that dark, visible gas cloud from here. But if your eyes had, say, infrared vision, if you even had an infrared pair of goggles and you looked up toward this particular region, you would see a lot of little tiny stars glowing through this background gas. So talking about that, we are going to go ahead and look down at the Swan Nebula. So going from the Eagle Nebula to the Swan, this is going to be just a short hop away. So if we have our view of the sky, you've got the Eagle Nebula up here, Swan Nebula a little bit further down, Trifid and Lagoon, all spaced out from our perspective. We're looking up here, and the galaxy stretches out in this huge arc overhead. So if you were actually outside right now too, standing here, looking down outside of the Godo, you would actually see the Milky Way stretching up. Now, unfortunately, it might not be the best time for viewing the Milky Way since the moon is coming up, but we were going to get a couple of our nebulas. Yeah, so those darker, denser parts of the nebula, those are exactly the really cool places where stars are being born. So I think we'll go ahead. And yeah, so these star these star-forming regions are pretty proliferant around the Milky Way. And as I was saying earlier about that infrared radiation, we can detect a lot more of these clouds using things other than visible light. So there's things like the Swan Nebula that we could look at that's very similar. All these things are going to be within the region toward the center of the Milky Way. And just for reference, that's very central points of the Milky Way, which would be, I think, just a little bit south of the Swan Nebula. We'd actually be able to see a supermassive black hole that is about 2 million times the mass of our sun. So this is kind of, at least on the short scale, kind of gluing the very inside of our galaxy together. This huge gravitational pull from this black hole creates this bulge of stars around it. And so these stars are basically locked in with this powerful gravitational force. And around all of that, there's so much condensing material that you end up seeing star forming regions and gas clouds like this. So here we have the Swan Nebula, really incredible views here. If we were to apply some more scientific studies like spectroscopy to this, you would actually be able to distinguish different types of elements present in the sample right here. So you'd be able to look at that cloud, and if there was a specific color of red or a specific color of green, and this would be measured precisely like to the nanometer, you would be able to associate that with certain types of atoms or ions that are present in that cloud. So this is a pretty cool study that chemists and astronomers use kind of in conjunction. On the closer scale, we can use satellites and other types of machinery to do spectroscopy on planets. And so we actually have rovers and satellites around Mars that we're kind of looking at analogous to being kind of salts and hydrated minerals like what we find here on Earth. And one of our astronomers, Dr. Jennifer Hanley, is actually involved in that research. So basically, yeah, lots of information can be gleaned just from the light that is bouncing off of these things, or in this case, radiating from them. So we'll go ahead and do another little nebula that's right nearby. And this is going to bring us down to, let's say, the Lagoon Nebula is what I want. So we've got a really nice view here. In fact, if you live in some really dark areas, and I know that this might not be all of us, but personally growing up here in Flagstaff, I've been lucky enough to always have pretty good views. And so I could even recommend a pair of binoculars and go outside. You would actually be able to see this little nebula in the sky with just those binoculars. And in fact, there's even certain places where you can see this unaided, without a telescope, you can actually see this Lagoon Nebula. So in any case, yeah, really beautiful kind of swirling gas cloud, reminiscent almost of, a painting. And it's really incredible. Imagine that this picture has moonlight kind of scattered through it. And with a telescope, about 14 inches across, something that, by the way, when you move upon its mount, it's feels relatively light. So I'm guessing that one could actually lift up this the telescope and instrument attached to it. Now, you probably wouldn't be able to hold it still enough to get a useful image, but the point being is that this is a relatively small scale telescope, relatively inexpensive sensor, and we're actually able to get some really incredible imagery of the sky. So I see that there is a question about the summer dolphin, and what I'm familiar with a dolphin is this constellation called Delphinus. And so you have a couple of constellations that are pretty much overhead at this time, part of the summer triangle. And the reason that it's called that summer triangle, there's 3 bright stars in the sky overhead, and they're kind of a wayfinding point. And just outside of this little triangle, you have Delphinus. And it's actually made up of a fairly closely clustered group of stars, but they're pretty faint. And so unfortunately, unless you were in, say, like suburban sky, or even like good suburban sky, you're not going to be able to see this, maybe even rural sky. So we'll go ahead and start our focus from all of these nebula here. So we've got this concept that stars explode. All of those gases could eventually condense into a cloud like this. Now, that's actually not what we're seeing. We're seeing this gas cloud actually expand out as the stars being born within drive those gases away with their pressures. All that light is sending out so much energy that these gases are going to continue expanding out. And so that actually brings us to little clusters that we can see in our sky. And so I guess right nearby, I know the wild duck cluster might be a little bit wide range for this telescope, but we'll go ahead and just bring up one of the closer clusters to this particular area of the night sky. We'll see a region of space where stars formed from a huge gas cloud like this, and they're slowly spreading out as time goes on. So, and indeed, we can actually see a pretty decent view of that cluster of stars right at the center there. So this is just basically a way that scientists can tell, astronomers can tell that a gas cloud was present here. All these stars have similar brightness to each other. All of the stars have similar compositions, and so we can learn a lot about where stars kind of come from and how they spread across a galaxy by looking at this composition. Now, I guess we'll go out kind of on like not one of our more common objects to look at through these interactive stargazings, but there's a star called Arcturus, which is actually up in the sky. It's going to be fairly low, but we should still be able to see it because this star has a very orange, distinct coloration to it. So yeah, we're in video mode. You can see our exposure time is just milliseconds, 34 milliseconds, down to 11 milliseconds. So we're really talking about just a fraction of a second for getting this information about that star. So the twinkling that you're seeing there, kind of that hazing around the edges, that's why stars twinkle to the human's eye. Stars are such small points of light in the sky that any little disturbance of that point is going to cause it to look like it fades all in and out. When we go to things like Jupiter and Saturn later on, you'll see some appreciable size to those objects. And although the very edges might blur and have this kind of hazing effect, the center stays strong. And that's why we see a planet as not twinkling as much as the stars do. So either way, we're looking at this kind of orange-red star. It's called Arcturus. In terms of the distance of objects we've looked at so far, this is by far the closest at 40 light years away. And what's really interesting about the star is that it seems to be part of a stream of stars that are passing around the Milky Way, kind of perpendicular to its regular axis of rotation. So basically, these stars came from some other region they're distinct chemically, so they don't have the same exact composition as all the other stars nearby. They're also moving a different direction, and so this is actually a pretty interesting star to look at, and just a way to kind of put that spectroscopy and where stars come from into actual learning. And what's really cool, I'll just mention one more thing, and then we'll get back to our stargazing, is that one of our PhD astronomers here was just co-authored on a paper that discovered something called the Phoenix stream. And this is actually something coming out of the center of our Milky Way galaxy, and it's a burst of stars, and a kind of a stream of stars that are coming out from this region. They look like they're really old, which is pretty interesting. But fact number two is that a stream like this is going to be pretty similar to the one that Arcturus is passing through. So we've got a question about atoms exploding. So for this part, I guess we'll go back to a good supernova remnant, or if that's not possible, maybe a planetary nebula. So I guess I'll, off the top of my head, I'll just say the Dumbbell Nebula sounds pretty good. So this isn't necessarily going to be a supernova, but it is a very large explosion, and it will do a pretty decent job of of tying this together. So, and one more question I'll address is that the summer triangle showing the mythology of the night sky, it basically contains three big constellations that are mostly involved with each other. And the view here is that these are going to be Greek. So you've got a swan, an eagle, a harp, and this dolphin nearby. And there's stories about, the swan representing Orpheus, who plays the harp. Maybe he went across the sea to claim, the best harp player. On his way back, he got stranded by pirates, and the dolphins came to save him. There's all sorts of different stories that can link them all together. So definitely some cool stuff. Check out our Stories in the Sky, or Sagas in the Sky series, also on YouTube, and you can learn a little bit more about that mythology. So we are going to go ahead and turn our view back to the central image here, that hydrogen toward the very outside, those kind of bluer elements toward the inside. And the question here being addressed here is, how do atoms explode? And so I guess in the traditional sense, I wouldn't necessarily say that atoms themselves explode, but there can be certain conditions. So we'll get there. When you have a big star, it's oftentimes composed out of hydrogen and helium, at least the very early stars in the universe. For reference, if we go back even a little bit further from these first stars, the universe was basically this very small, dense region of space, lots of energy, lots of little particles moving around at high speeds. Sometimes these speeds were so high that you can't quite get light from one place to another. And so this is when the universe is basically opaque. But anyways, as it expands out, eventually light can pass through that universe, and eventually that energy and those atoms cool to the point that energy expands. So same energy distributed across a larger area, you've got a little bit less energy per area. And that stuff can cool into hydrogen, into helium, and that births the first star. So once these stars form, they're super hot, and they can actually take separate atoms and squeeze them together under, trillions of pounds of pressure per square inch, millions of degrees Fahrenheit, and it'll actually cause these atoms to smash together. So that's the opposite of these atoms exploding. Now, stars can basically mash little pieces of atoms together, bigger and bigger and bigger. The bigger the star, the heavier that atom can be built, all the way up to iron, at which point there's no longer energy released from this atom being, forced together. Instead, it takes more energy to add extra pieces, extra neutrons or electrons or protons onto this atom. So at some point, you end up with these stars running out of energy, and they kind of condense down and then they explode. And that's when you have a supernova. So the iron-rich core of a star that is about to go supernova suddenly explodes outward. There's this huge amount of particles and material and energy and all this stuff exploding outward. And these little pieces of matter can actually reach like 99% the speed of light. So imagine a little hydrogen or a helium crashing into an atom out here. It can sometimes get stuck there. And so that will build a little bit larger atom. That will build a little bit larger atom. And so there's actually cases where naturally occurring in these supernova explosion, atoms come head on and create things like uranium and plutonium. And these atoms, being radioactive, will spontaneously kind of explode or decay, breaking into separate pieces. There's even probably rare cases, especially in these stars, where heavy atoms come together with such force that we're able to form, things unheard of here on Earth, things that we couldn't even recreate in a lab here, one of those big cyclotron, things like CERN. So either way, we're going to go ahead and look at, let's see. So maybe, we're going to address one more question. Number of constellations in the sky, there's 88. There's divided between the northern and southern hemisphere. So basically there's a whole group of stars that we can't see above the equator because the Earth gets in the way. But moving on from there, we've got the Western Veil that we already saw. Well, we already saw the Veil Nebula tonight. So we'll kind of move on from there to some of the closer objects. So we talk about those atoms exploding, being created in these supernovas. These planetary nebula, as those atoms, gases expand outward, they are going to kind of coalesce into other nebula and maybe form new stars and planets. So I guess we could go to maybe one more relatively nearby star forming region. And I guess a good example of this that we didn't quite do yet would be the Trifid Nebula. So these regions, and I don't know 100% off of this, like on this nebula in particular, but there's countless cases where these nebula are actually giving birth to new stars inside of them. And so that's what we were talking about. Now, sometimes these stars can have enough gas around them to actually form planets. And so we'll get a chance before too long to actually see some of the planets within our sky that were formed from a region like this. So imagine sometime long, long ago, billions of years ago, we estimate the sun's age at about 4.5 billion years. The sun formed in a little tendril of gas, maybe one of these dark clouds like we can see here, where that gas was cold enough to condense down and form stars. So those little kind of spreading dark clouds, those veins of condensed gas, that's where the stars are coming from. Now, in certain cases, we've actually been able to detect gas rings and planets and things like that around those stars, that would be an exoplanet. And so for us, at the same time as the Earth's formation, rather the sun's formation, its planets all kind of formed around it too. So we can go ahead. So yeah, we just got a request for the Trifid, and that's exactly what we are checking out right now. So one thing we'll look at right now is going to be the hand of God, I guess. I'm not 100% sure if, well, actually, never mind. We're going to skip that one. So that, I think that's within the Eagle Nebula. And the problem with some of those like well-known objects is that you can't necessarily see them with the common telescope. Like, for example, the Horsehead Nebula might be something that we've heard of or we may be familiar with, not exactly accessible by all types of telescopes. So we're going to go ahead and look at the M30 right now. So that's going to be, and then we'll look at maybe one or two requests, but we really want to get some planets in here. So we'll do that before too long. So one more of our little globular clusters. These places, you know, we're talking a little bit about planets right now. There's an imagination that if you were to find life somewhere else in the universe, it would probably be in something like this. And so, in fact, M5, I believe it was, but it could have even been M15. Was an object that we sent a message to using that huge Arecibo telescope down in Puerto Rico. Unfortunately, it was just damaged by a storm or a cable, I think. So it's going to take a little bit of time to restore that. But anyway, they use this telescope to beam a message off to a distant cluster like this, because we imagine that the stars there, since they are relatively old, are actually close enough together and possibly, old enough, they would have all these planets where interstellar travel would be relatively easy, and a spacefaring civilization could probably come out of here. So either way, looking at these big clusters can give us insight into, what else might be there. Just within one of these clusters, there's sometimes hundreds of thousands of stars just like the sun. And any one of those could have planets, which will bring us into a really good view of a couple of our last objects, which will be the bright solar system objects in our sky. So we've got some really good views of probably Jupiter first. So that's one of our planets that's going to be coming up just a little bit west of south. So right now is a pretty good time to see it at a reasonable viewing hour. About a month ago now, there was something called the opposition of Jupiter. The opposition of Jupiter is when it gets on the opposite side of the solar system than we are from the sun. So basically, it's as far from the sun as it can possibly be, as close to us as it can possibly be, I guess is what I meant to say. And in that case, that planet appears a little bit brighter and a little bit better resolution. So we can see a little bit of the clouds on Jupiter. This is a live view, so that little changing on the surface isn't necessarily clouds on Jupiter. That's just atmospheric effects, but those two vertical bands are indeed features that you can see on that surface. Now you're looking at something like a cloud structure that's 500 million miles away right now, give or take. Maybe at this point, it's probably closer to about 420 million miles away. And you're actually seeing structures that exist on that other planet, sort of like oceans and continents that exist here on Earth. And so I think that we're zoomed in pretty high here, but if we go ahead and just scroll back out on our screen a little bit, we can actually see a couple of the moons of Jupiter here too, if I'm not mistaken. And that's actually going to provide us some insight into both what Galileo saw back in very early days of telescopes, but also kind of some insight into where NASA is planning to go next. So one of these moons is called Europa, and it actually has an icy crust with a possible liquid ocean underneath. And so we're really looking forward to exploring some of these alien moons around Jupiter. We could go to Saturn real quick to kind of compare our views here. So we've got Jupiter there with its 4 kind of distinct moons, nice and planar in its orbit. While we're moving our telescope, I'll just explain that a little bit. We've got a planet in the center, and it's spinning very, very fast. And this will go into a discussion about Saturn's rings as well. So there you've got this planet. It's really big. It's made of gas. It's going really, really fast. And it's spinning so fast, in fact, that it only takes about between 10 and 12 hours for a day to pass on Jupiter and Saturn. So you're talking about these really, really fast days. I mean, if you were standing still on the surface, you would go from day to night to day to night to day again, all within the span of one Earth day. So we're looking at Saturn here, but Jupiter too, they're spinning really fast. Now, what happens when something spins really fast is it becomes a little bit oblate. And so even the Earth is what we refer to as an oblate spheroid. And that actually tends to gather a little bit more mass toward the equator than anywhere else. So anything that's caught in orbit around this thing is going to be more heavily pulled into the center than toward the top and bottom. So it will eventually settle out into that really low energy orbit. The rings of Saturn are kind of in the same case. The moons of Saturn will also extend out in that same plane. And it's possible that one of the moons of Saturn, as it was orbiting around, very icy moon, got so close to Saturn that its back and front sides were subject to different gravitational pulls, and that moon actually shredded apart and turned into those rings. Now you can actually see a whole collection of those moons, some very close to Saturn, some a little bit farther away. Now that one way up toward the top is going to be called Titan. So you've got Saturn and its rings down here, a couple of moons going around it, but then way up here is Titan, which is another planet that's studied by Dr. Jennifer Hanley, not only Mars, but Titan as well, and some of the ices that are present there. So this is a world where there's actually an atmosphere similar to what we have here on Earth. There's air, there's gas, there's stuff you can potentially breathe. Now, in this case, it's much too cold for our lungs to handle. It's methane gas. Gives a distinctive orange color to Titan. So if you look it up, but there's actually lakes on the surface. There's ice-capped mountains there. There's rain of methane. In all these cases, methane ice, lakes of methane, methane rain. And it's a really interesting world to explore because of that. Now, the atmosphere there is so thick and the moon so small and gravitationally weak that a human standing on the surface could flap our arms and we'd actually be able to fly through the atmosphere of Titan. So we've got maybe about a couple minutes left to just kind of phase out of here. So we got a really good chance to see those closer objects. I guess kind of as a, a last object, we'll go to the moon, which is an excellent view. Really my favorite thing to look at in the entire sky. So it would be great to be able to see something like Mars. Maybe if you tune in and not too long, maybe 3 or 4 weeks from now, Mars will actually be steadily rising on our horizon, so that by the time this 8:30, 9 o'clock rolls around, we'll actually get a chance to see that red planet that Lowell Observatory is so well known for. So one of the kind of lesser known things about Lowell Observatory, but definitely coming up more and more as we celebrate these moon landings, is that we actually had a team of scientists and astronauts and artists up here mapping the moon for the Apollo missions. And the astronauts all got to come to northern Arizona, train here. And Gore was a huge architect of the spacesuits. USGS trained all the astronauts on what to bring back from the moon, and so just a lot of kind of cool ties between Lowell Observatory and both the moon and Mars. So we're going to go ahead and start wrapping up here soon. One last question I see is, why does Mars appear to be above the ecliptic? Well, as I mentioned, things that are spinning tend to kind of bulge around the equators. That often causes objects in orbit around them to flatten out, become planar. Now, from our perspective, maybe the difference in tilt between Mars and the Earth, which may not even be, 1 or 2 degrees. If you're talking about the vast distances traveled here, even 1 or 2 degrees can create a pretty appreciable tilt from there. So again, thanks everybody. We've got the moon as kind of our last object here, a couple of awesome craters. All those astronauts got to land on the side that we're seeing here. Possible moon base going up in 2024. We're looking at, a lot more public, or rather private launches. So definitely some really cool moon science to look forward to. So again, thanks everyone for tuning in. And I would say, I think we could probably wrap up there. So have a great night, everybody. Don't forget to tune in to some of our later programs. International Observe the Moon Night, continuing with these video series. So lots of support from us here at Lowell Observatory to everybody's interests about space. So if you ever have a question, email us, call us, and we'll try and get back to you about that. So thanks everyone.